Uh-oh, can't detect the owl. Poopers.
Hello, David. I'm gonna run and see if the other David is in the graduate student office. I also had something on the printer for me.
Okay. See you in a second. How's life, Claudia?
Pretty good. How about you?
Honestly, good. It was kind of down for a while, but now it's back. It's coming back up. It's pretty good. Um, I mean a lot of shit.
Oh.
Sorry, that's like I don't know. Like I feel like it's almost too much to get into, but I wasn't really killing it on the school front for a while. But I'm back on the horse, so it's cool.
That's good.
I got dragged into I got really into this kind of depressive doomer cycle too, just about like everything. That was a little brutal.
Well, we
Like,
could kind of follow like what you were saying in class, so I'm glad you're feeling better.
yeah, I mean, you still gotta acknowledge this realities, but you know, pivot on the point of view and all that.
David will probably sit here, leave it on to him. So I'm just kind of handing out some little cheat sheets from today's lectures that help answer, okay, what test do I want to do for associations? What test do I want to do for, statistics? And then, with the correlations, the association, how do you interpret them? +1, -1, 0, things like that. So you have it in the lecture, and the lecture is already in the folder for this week, so. Yeah. All right. So let's see, Lily yet. I don't want to waste people's time, so I'm gonna start sharing my screen. I'll remember to share my screen this time, haha. All right, so let's start with just kind of some housekeeping stuff. Hide these. So you should be seeing Blackboard. Can you guys see it with the lights? Yeah, okay. All right. Okay, so we're getting towards the end of the semester here. It's barreling down here. I have added, future weeks here. Next week, we're gonna talk about, disseminating research, so I believe it's chapter 17. I don't have anything in there right now, but if you go to this week, you'll see for next week, to read chapter 17, communicating research results. This kind of leads into your presentations that'll happen the last week of class. You guys are gonna give presentations on your capstone proposals. And there's this journal post kind of to briefly outline your data analysis and methods. A lot of you have done this already in your submitted research proposals. But as you've seen, things change. You keep refining your questions and stuff like that. So, there might be some changes from what you've submitted. I also, made quite a few comments on people's research proposals to just think a little bit deeper about where they're getting the data from, what that data might look like, and how they're gonna analyze it. Marie's kind of a little concerned because, you're probably not gonna have a huge sample size. So California David hopefully will get a large enough sample size because we're paying thousands of dollars to send out a survey to the residents on the Kenai Peninsula. So we're hoping 500 sample sizes or above. You're probably not gonna interview 500 people. And so it might be difficult to do any statistical tests, with the size that you have. You can do the basic statistics that we've been showing, pie graphs, charts, things like that, kind of even what is the mean, and scores. But as far as doing like statistical tests, you probably won't have a robust enough sample size. I mean, I have done it on a sample size of like 50, but that's a pretty small sample size. And the same with you, David.
Yeah,
I think Marie's kind of talked to you about that.
Yeah, I might already have all the data I'm gonna get
Okay,
potentially.
okay. Yeah, and so, like with yours, where you're looking through, say, literature and say you're doing an analysis of, hazard mitigation plans. And if you're going through and coding them as, yes, this has this, no, this doesn't, and say you have a row for each plan and you're like, does it talk about erosion? 0, 1, 0, 1, where 1 indicates yes, 0 might indicate no. Then summary statistics are what percentage of the plans I reviewed talked about erosion or talked about wildfire, included TEK. That would be the kind of numbers that you would be crunching with something like that.
Okay,
Yeah, but not like these analyses that we're doing with SPSS.
yeah.
Yeah.
We talked a little bit about it.
Yeah, and people have been fearing the statistical analysis. And the thing is you probably won't be getting too hardcore into statistical analysis. But this is good to know, so when you're looking at other people's reports, when you get to be managers in your jobs, you can say, well, you're full of BS, go back and do it. You can understand them. Okay. All right, let's see, and so there's that, and then for week 15, I did put in there the research proposal presentations. And the homework that you guys have for it, so it's a guideline as far as what is expected. You'll be in class here, and you'll be giving your 10-minute long, no more than 10 minutes. Maximum of 10 slides to present what your research proposal is. So title page, introduction, background, discuss the major work published on your topic. So you don't have to cover all of, your literature, but these maybe are the general themes that I looked at and the key point, takeaway point. Significance, methods, data collection, analysis, the products and the timeline. Those are kind of your 10 slides I would like to see in the presentation. So it kind of takes the guesswork out of what you guys have to do. Yeah. And so that is in this week, 15 proposal and presentations. And so if we go to, the, syllabus. Just looking through it. I just kind of want to review. Your final research proposal completion is worth 10% of your grade, so it's worth 100 points total. I'm not sure in here if I think I say when it's due, but let me just check. Due May 6th, so that's when you should submit your final research proposal. And again, when you look on Blackboard, you know, we have the research proposal information here. So it's gonna be the whole shebang, kind of using the comments and feedback that you've gotten over this semester, and also any advice you've received from your advisors, you know. And don't be surprised if things change again after this class, you know. Over the summer, things might evolve, but this should be a nice skeleton outline of what you're gonna do. I really strongly suggest you not change your topic too dramatically. You know, there's one person here who, she changed her topic from when I taught this last spring, and probably gonna delay her a year. So try to stay the course. Okay. All right, any questions? Okay, I don't see any. So we'll get into it. Alrighty. So we discussed that. All right, just kind of, you know, this review, review of measures of association. So the purpose of these tests is to, you know, look at, is there an association between the variables? You know, might age of a person be related to income, or might, you know, education be related to, how religious a person should be? So it's not testing for the significance of that relationship, it's just saying, is there a relationship and how strong might it be? So, and we typically, you know, use the lambda or gamma, depending on whether it's nominal or ordinal. If you have small sample sizes, the tau A or B is better, and this should B or C. And these values usually range from 0, you know, to 1. In the case of ordinal, you can have -1 and you can have +1, because there can be directions to it. Do they vary in the same direction? Do they vary in different directions? Okay. And so, this is some of the cheat sheets that I just handed out today in class, David, California David, so people have them when, we ask questions about them later on in class. So, again, the associations, 0 is no association, -1, they might differ in opposite directions, one goes up and one goes down, +1, perfect relationship, between the two. Okay.
I
And then, yeah,
have a quick question about that. In some of the other tests, I'm trying to remember which one it was. I think it's the gamma that will give tau number. No, sorry, all these Greek letters. Anyway, it'll give like whole number, large number correlations. Like they won't be percentages or decimals. And I don't know. It maybe if I'm running it wrong, or I don't know, but I'm pretty sure it was the gamma that was giving me that.
huh, okay. Well, let's see, I'm just gonna write it on the board, and how about when we start to go through some of the examples today? In addition to doing our statistical tests, why don't we also throw the gamma in there and see what the gamma results are? Do you have a specific analysis you want us to try?
I think I was getting it in one of the homework questions, but I was trying to pull up my results real quick and I wasn't seeing it. But no, that's okay. Well, we'll see if it comes up.
Okay. All right, review of the association, we talked about linear regression and how you can get the Pearson's R is the score with linear regression. That's the review the association, and then the R squared. Does anyone remember what the R squared represents?
That's the percent of variance that's explained by the model.
Yep, exactly right. So, if you have an R squared of, 10 or 0.1, 10% of the variation is explained by your model or, that parameter, if it's a single parameter in your model, that variable. Yeah, exactly right. I think that's one of your questions on your homework this week. So, okay. And then, obviously the linear regression equation. Again, with all of these, very important to figure out what is your independent and what is your dependent variables. I like to think of it as my dependent variable is going to be influenced by the other variable. So if I change X here, I'm looking to see how Y changes. Okay. All right. Okay, so, inferential statistics, these, tests for statistical significance. So what you mean by that is they'll tell you how likely the results, from a random sample are due to chance. So how likely is it that, let's see, what are some of the things we looked at last week? Trying to remember. We had turtles. Didn't we have turtles?
I only remember the cats and the will to live.
Cats and what?
Will to live.
Will to live. Okay, okay. Yeah, so with the cats, it would be testing like out of a random sample, how likely is it that, cats would influence a person's will to live? So if, the test, was significant, say at the 5%. So, out of 95% of the people that you drew from 100, if that was a significant relationship, 95 of the respondents would say, yes, cats are important for my will to live. If it's not significant, then usually it's, due to chance. So when you're looking at a statistical test, you're testing how different are your results from the null hypothesis. So in the cat instance, the null hypothesis would be there's no relationship between people's will to live and owning a cat. That would be the null hypothesis. So if we got, say, a p-value that was large, we would reject that statistical test and say that, yes, there's no relationship between cats and the will to live. So, in this example, the p-value over here indicates, very unlikely observations. So your p-value or probability value is a number describing how likely that your data would have occurred by random chance. So small p-values mean it's probably not random. There's something significant there. And I'm sure you guys have all been doing your literature review. The word significant is very special. It's usually reserved for statements regarding statistical tests. So another example is a hypothesis. You are more likely to be religious if you're a man than you are a woman than a man. So the null would be that there's no association between gender and being religious. And so a p-value of 0.05 and below usually means that you reject the null hypothesis and there is a relationship, a significant relationship. So usually this cutoff here is 0.05. Okay. It can be kind of confusing. But so with the p-value, how different the results are from the null hypothesis. A p-value that's, 0.1, there's something there, but it's not statistically significant. P-value of 0.05, that's right on the edge of being significant. A p-value of 0.01, even smaller, that's pretty significant. So the size of that p-value can indicate the strength of that relationship. And I mean, that's kind of, similar to the Pearson's R or the gamma or lambda. That value, the size can indicate the significance of the relationship. And you typically do them both. You do a measure of association and you do the statistical test. And I'll show you statistical tests today. Okay, so getting to the size, what does it mean? So when we're talking about p-values and running a statistical test, really you're getting at how generalizable are my results to the public. I can run a test and say, yes, there's a significant association, but can that association hold up to my population? It might hold up to the people in this classroom, but would it hold up to all UAA students? That's when you run a statistics test to see if you can generalize your results. Clearly a sample size of 2 here in class, we couldn't do that, or 4, too small. So if your measure of association is strong, so that gamma, lambda, Pearson's R is strong, and your statistical test is strong, so you have a p-value of 0.5 or less, then you fall into this. It improves the prediction, there is a relationship, and you can generalize it to the public. So like in California, David's example, if we're doing these surveys on the Kenai Peninsula, and this comes up, our results can be extrapolated to all the residents in the Kenai Peninsula, if that's our sample size, not just the 1,000 households that we survey. Okay? The next one is, if your gamma lambda is strong, but, you just can't get that p-value, then yeah, it's important. There is a relationship there, but it's not strong enough to say that the rest of the residents on the Kenai Peninsula, are gonna behave this way. We could say something's there, but close but no banana is what your book says. If you have a weak association, but the statistical test is significant, yeah, it's a little bit of help. There is a little bit of a relationship there. Yeah, you can generalize it, but it's not really that important of a thing. It's weakly, this weakly affects your predictor. So yeah, like say you had age or something like that, and that came out to be weakly associated, but in your model, it turned out to be 0.04. So yeah, it's significant, but it's not the best predictor of your results, of your dependent variable. And then if they're both bad, go back to the drawing board. Neither of them help predict, and you can't generalize it to the public. So this is another key slide in trying to interpret your results. Any questions on this?
I had a question, but I think I can answer it, which is that we haven't done statistical significance tests yet. That's a separate step.
That's today.
Okay.
So that's today. We're gonna do like ANOVAs, t-tests, things like that. Chi-square, chi-square is a big one when you have frequency tables. So we're gonna do this today. So where do you start? Again, the questions, what is your hypothesis and what is your null hypothesis? So in order to run a statistical test, you've got to know, what am I testing? And say, if I reject my null hypothesis, what does that mean? So always come up with what's the hypothesis and what's your null hypothesis. That's going to drive the statistical test that you use. The second thing that people talk about are independence. Are the data independent? And by that we mean, are we sampling the same person over and over again? If we are, then the data is dependent. So you can see this, we're sampling the person over and over again. If we looked at people who are on vacation, we might have said, how's your stress before vacation? And then we might have done an exit survey and caught them as they're leaving the airport after their vacation. Dependent data. If we just did random people before and random people after, that would be independent data. Let's see, Claudia, in your example, say you had really stressed out lawyers and you took them and said, go to a massage place, and then you interviewed them afterwards. That would be dependent data because it's the same person before and after. Okay. And then, also what types of data are being measured and used in the analysis. The same thing, when we were doing the association tests, is it nominal, ordinal, interval, or ratio? That influences what statistical tests you do. And in your homework, for the questions, I'll walk you through these. Please tell me what's the null hypothesis. Tell me, what type of data are being used? What's the scale of the data? Okay, and I don't know, I made this up. It's just kind of a funny way to look at how to tell different types of variables. So if you're looking at beards, categorical might be, do you have a beard? So yes or no. Ordinal might be what shade of red is your beard? It's light red, pale red, gray. Non-red was red but faded, something like that. And a numerical example of your beards could be how long is the beard? That is like an insane beard. Or how many times a week do you shave? You can't really halfway shave. You look really bad if you halfway shaved. So if you shaved, it's usually yes, I did it once, twice, 3 times, But your beard length, you can get down pretty fine with your beard length. Yeah. So, and I mean, this also, the point of this is it shows, like I was talking to Claudia before class, you can have a data and you can make it different types. With Claudia's example, we were talking about how the length of sentence, that's one of our data points. And sometimes that length of sentence might not be what a person actually serves because they can get out on good behavior. They could have it waived. You don't know. So that actual number might just be bogus. Instead, you could turn it into a nominal data type where it's, yes, they had they were served a length of time. No, they got off and they didn't have any time served. So you take away that, I don't really know how long they served, and you turn it into a yes or no. So ways to change the types of data that you have. Okay, and so with a hypothesis, we're typically trying to reject the null hypothesis. If our p-value is significant, 0.05 or less, we reject the null hypothesis and we accept our hypothesis. We're saying this is less than random, something is going on here. Okay, so I would like you guys to take like 5 minutes and, think about a hypothesis and a null hypothesis for your capstones. Doesn't mean you're going to do them, but just kind of something associated with the data that you've been looking at. Let's do it till 6 here. All right. See, Claudia, what do you have?
So for my hypothesis, I wrote an increase in caseloads among public defenders causes an increase in jail time for the clients they represent.
Okay.
And then for the null, I wrote, there's no relationship between caseloads among public defenders and the jail time their clients get.
Okay. Okay, yeah, that's correct. So in this situation, what would be your dependent and independent variable?
So my dependent would be the jail time
Mm-hmm.
and the independent would be the number of cases.
Yep, because you're looking to see how caseloads influence jail time. Yep. Mm-hmm. And more than likely, this would be, what type of data would this be?
Discrete.
Yeah. Discrete, or, I think interval. Yep, and then this one we talked about could be a continuous, it could be nominal. Yeah, something like that. Okay, all right. Excellent. Hi, Lil, I see you've joined us. I asked everyone to come up with a hypothesis and null hypothesis for their research projects. I mean, it might not be something that you do, but just using your data and trying to come up with something. So how about Claudia, or sorry, David in class?
For my hypothesis, I predict that local knowledge makes a difference when creating hazard mitigation plans.
Okay, all right.
And then the null hypothesis is, I predict it does not matter if you include the local knowledge to hazard mitigation.
Okay.
Is that correct?
Yeah, so local knowledge makes a difference in hazard mitigation plans, okay? And the null would be, no, it does not. You know, one difference between yours and Claudia's is that makes a difference is very vague. How would you assess makes a difference?
Maybe just the rates at which they receive funding, what gets approved, which plans get approved and which don't.
Okay, okay, so it could be like, you know, maybe community approval rate?
Yeah,
Okay. Yeah, or it could be, you know, the percentage of times it actually gets used when you have a situation where you should be using your plan. You know, did you use it or not?
yeah.
Something like that. Yeah, yeah, okay. And then, what kind of variable would local knowledge be?
That's the independent variable,
Okay,
if you have local knowledge.
yeah. But like what type of variable? Ratio, let's go back to our beards. Continuous, discrete, ordinal, nominal, kind of what type of variable would that be?
Maybe ordinal? I'm not quite sure, yeah. Maybe.
Probably it would be. Let's put a little on the spot, she just got here.
Sorry.
So, local knowledge makes a difference in hazard mitigation plans. What type of variable do you think that would probably be?
Local knowledge, would that be local knowledge would have an effect? Would that be ordinal? Wait, no?
It would be ordinal if you were like, did it have a little local knowledge? Did it have a lot, you know, a lot of local knowledge? Did it have an extreme amount of local knowledge? Then it would be like ordinal if you did something like that. But if you just ask, does it have local knowledge? Does it not have local knowledge?
Okay, then it's nominal, right?
Yes. It would be nominal.
Okay,
Does it have it? Does it not? You're just complicating yourself if you try to say, how is a lot, you know, how much is a lot of local knowledge? How much is a little, you know? Yeah, people would then argue with you as far as whether it's a lot or not. So it doesn't have it, doesn't. Yeah, no.
No.
Okay, all right, how about California, David? What did you come up with?
Excuse me, I just took a bite of a sandwich, but my non-null hypothesis would be that. Do you want me to start with the non-null or with the null? Non-null would be that there is a relationship between the cost benefit, I guess the result of a cost benefit analysis of a fuel break and the type of fuel break that it is. That would be the non-null. The null would be that there is not a relationship between those two.
Okay. Okay, all right, so, like a result from a cost benefit analysis.
Yeah, I mean that's a little big, but like I guess like pick a. I haven't actually done one yet, so I'm assuming at the end you get some kind of number.
Okay, so we're thinking of something that maybe might be, are you thinking maybe continuous?
Well, yes, continuous in the. I mean, dollars are continuous more or less, right? At a certain
Yeah.
point, they become discrete, but yeah.
Yep, okay, all right, then what, type of data would be your fuel break, your types of fuel break?
That would just be nominal. There'd just be two types.
Yeah. Yep, okay, all right, okay, yeah, and yeah, like you said, the null hypothesis would be there's no relationship at all between the cost benefit results and the type of fuel treatment. So, yeah, exactly right. Lil, you got here late. Did you want to take a stab?
Sure. So we are talking about putting together a null hypothesis, right?
Yeah, a hypothesis and a null hypothesis. So I'm just trying to see, like, a hypothesis is that there is some type of relationship. Usually the null hypothesis is that there's no relationship.
Okay. So the hypothesis I put together is that, my hypothesis is that there is a difference in the challenges faced by health policy administrators in Anchorage when adapting communication strategies to accommodate the city's diverse cultural landscape. And then the
Okay.
null hypothesis would be that there is no difference between the different diverse groups.
Okay. So I wrote health administrators influences the type of challenges.
No, so the different groups, like the cultural diversity would influence the challenges, yeah.
Okay. All right. Okay. Okay, cultural diversity influences the type of challenges, and then the null would be that there's no relationship. Okay, so, the next is to think about the type of data, and so your cultural diversity, what, kind of type of data are you thinking about for that?
So for the cultural diversity, I was thinking of getting some demographic data in Anchorage.
Mhm.
Yeah. Of like possibly like the top groups or I don't know if that would be appropriate. Like
Well,
kind of
in one of your papers, I mentioned that there is actually a diversity index that's done by the
Right.
census. Yeah.
Mhm.
So in general, probably this is gonna be, some type of continuous variable, a percentage of people who are non-white or this diversity index, right? Okay, so likely it's continuous. I can spell it. Okay, and the type of challenges, how would you quantify that one?
Would that be nominal because there's not like a like it doesn't increase or decrease by any degree. I think the challenges are very different between each other.
When you're looking at cultural diversity and you think it's gonna affect the type of challenges, I might, think more of, it might influence the number of challenges that you face. So I would think in areas maybe where you have higher cultural diversity, there's more challenges maybe that are reported by health practitioners that they've got to address. And so that would be something to me that would be like discrete. People in these areas have to deal with 10 different challenges that they listed in our interviews, our focus groups, versus these other people. They only got to deal with, do people look at their Facebook or something, a lower number of challenges. Does that make sense?
Yeah, that's actually a great way to look at it.
Because, you weren't on yet, but we were talking about how, we're going through all this statistics and all this scary numbers and p-values and stuff. But in reality, you probably aren't going to have the sample size to do a lot of these statistical tests. Marie says 400 or above is the sample size to do statistical tests. I've done them with 50, which is kind of low. But more than likely, it's going to be, doing some descriptive statistics. So making like maybe bar graphs or counts of the number of challenges, or what percentage of, people mentioned this certain type of challenge. So visualizing your results is more than likely what you're going to be doing in coding, that coding exercise Marie did with you. Again, I'm going over this stuff because it's important for also be consumers of the literature. And when you're a boss, you can tell people whether they're doing it right or wrong then. Okay. All right, so, there's parametric and non-parametric tests. This is just something to be aware of because statistical tests often have assumptions. They assume that your data is normally distributed. They assume that the variance is equal among your groups and that the data is independent. So if these assumptions are not met, then you're likely going to do non-parametric statistics, which are perfectly fine. They're just a little bit weaker. So they might not find results that the parametric statistics find because it doesn't have as much power. And you can do tests to look at if your data is normally distributed. That's the bell curve. When you do your histogram, do I have a nice bell curve? Is my data normally distributed? The variance, I'll have some pictures coming up, but think of a picture of a bell curve that's really peaked and one that's really wide. The one that's really wide has a lot of variance. The one that's really peaked has a very little variance. So those two samples would have different variances. That's what that means. And the data, are they independent? We just showed that with the people, are you asking the same person over and over again? Or are you sampling different people? Yeah. So here's the example of the normally distributed data. You can look at this probability distribution or histogram here. Normal QQ plot. Back from statistical days. That's a way to see if your data is normally distributed. It should be, all the points should be along the line. So that's a way to explore that one. There also are tests for whether your data is normally distributed. This Shapiro-Wilk test is the one that's most commonly used to look at whether your data is normally distributed or not. So, those are some tests. All right, variance. So here's the example I was talking about where this group in blue has a much larger variance than this group in yellow here. And I guess there's a test for everything. You can do an F test, a Bonnet's test, a Levine's test, which we'll do a Levine's test today. To see if your data, the variances are equal among your groups. So say if we were looking at something between the sexes, this would be a histogram of your males and females to see if the variances were equal. Okay.
If the variances are different, is that one, does that mean it's non-parametric?
Yep. Mhm. Exactly. Okay. All right, and then, for, your book chapter, they go over the, reviewing the sampling concepts. Cause really sampling is very, very important when you start to talk about statistics. We've already seen it's important to identify what your types of data are. It's important to identify your sample versus your population. Your population of interest. If your statistical test is significant, then you can extrapolate your results out to your entire population of interest. Okay, so with the Kenai Peninsula, the population would be, say, the residents on the Kenai Peninsula, property owners. A census, the whole count of the whole population. We're all familiar with, the US decadal census. They're trying to get everyone. The sample is a subset of the population. So if we're gonna do 1,000 households on the Kenai Peninsula, that's the sample size. Maybe there's 4,000 people who live on the Kenai Peninsula. That's the population. Statistic, characteristic of the population based on the sampling results. So, what are we looking at? Are we looking at, whether, people who live on more expensive lots are more likely to have fuel treatments next to them? Are we looking at that statistic? Are we looking at whether people have longer jail time, if they have burnt out lawyers? Kind of those are your statistic. The parameter, that's the inference made regarding, so your range of the statistic, your confidence intervals. So when we did that linear regression, that would be kind of that line that gets fitted with your linear regression. And then with a linear regression, you can have confidence intervals around it. I'm sure you guys have all seen, a linear regression picture that has confidence intervals around it. Or you've seen bar graphs, with standard error bars on it. The generalizability. That's, is the p-value significant? Can we generalize it up to our population of interest? And that also gets to statistical significance. Is the result by chance or not? So, I think don't overthink these. I mean, they kind of make sense and we've seen them before, but just technical terms. Okay. So p-value, that stands for probability value. I mentioned already 0.05 is typically the rule of thumb. If it's 0.05 or lower, it's usually significant. And that means with 95% certainty, the results reflect the population. It's not just a quirky example. So let's say if you looked at sex and height and it was significant, and typically males are taller than females. So if you sampled 95 people out of that 100, and they're males, typically those will all be taller than the females. Because you're statistically significant that height is related to sex and males are taller. As an example. There's lots of other factors that affect that, obviously. It's important to remember that although the results may be statistically significant, they might not be important. This is where it comes into using common sense when you're putting together your statistical tests. Okay, we could have do people who own cats have fuel treatments next to them? Okay, maybe it's statistically significant, but do we really care? Can we do anything about cats? If we give people more cats, will they be more likely to get a fuel treatment? Probably not. There's probably something else driving that. Maybe they have more money to afford to take care of a cat. So you can have a statistically significant result that's just not really important. So confounding factors are important to remember. And I also mentioned that, significance, that is only use that word in your papers when you're talking about a statistical result. I give other options here if you wanna say substantial, important, notable. Monumentous seems kind of dramatic, but you can use those other words when you wanna talk about something not related to statistics, or when you're describing, say, charts, descriptive statistics. Again, measures of association are different from the statistical test you're gonna do. Okay, so that gamma, that lambda, Pearson's R are different from p-values. Garbage in, garbage out. So, I mean, if you're putting crappy data into a model, you're gonna get crappy results. Yeah, and that's where admitting, you know, what biases you have in your data, what limitations you have in your data. I mean, you can throw anything into a model, but if it's not good data, then you're not gonna get good results.
I
Okay.
have a question about the cats and fuel treatments example. So, like, if you found that correlation, but you could explain it by like the intervening variable of say like wealth, right?
Mhm.
Is the way to say that in this language, is that what we're talking about when we talk about like independence? Like when you measure independence, you'd be like, oh, these like, it's not that if you combine cats and wealth, you get a better measurement of fuel treatments. It's that those two variables, like the independence of that variable is bad or wrong or low or something.
Yeah, you would probably do like a correlation matrix and see if wealth and the ownership of cats is correlated. And you know, if it is correlated, like people who have more money are able to have cats, so they have more cats. If that is correlated, then yeah, you don't have independence between those two variables and you've got to drop one. You can't have them both in your model because then you have something called multi-collinearity. One of them has to go. And it would probably make sense to drop the cat variable.
Got it. So like causality between your independent variables is the like, that's what we're talking about, but the inverse of what we're talking about when we talk about independence.
Yeah, that, exactly kind of what you said, that, causality association among your independent variables that you're trying to predict. You don't want to have variables in there that are kind of representing the same thing. So that's why you usually see like a big correlation matrix. If people have a model and there's lots of variables going into it, they actually want this with my McKinley paper. They want to see a correlation matrix to see if these variables are correlated. If they're not, then they're each giving new information, new insights. If they are correlated, then there's some repetition going on in there. And then the next step would be, I will run the model with one of the variables. I will run the model with the other variable, and I will look at a change in AIC scores or the change in MSE, the error value, to see which one has the better model fit. And then you go with that one, but you also have to use common sense. I don't care if cats is the most important. That's not helpful for managers. That's not helpful for people. So common sense has to play into this too. Does that help, David?
No, definitely. I wanted to make sure I was clear on that. But definitely. Are we gonna do one of those did you say correlation matrix? Are we gonna do a sample of one of those?
I don't have one planned, but we could, if we have time, we could play around and see if we can figure out how to do it. So,
Cool.
okay. Yeah, I think it'd be neat to try and figure out how to do. Like, yeah, there's so many things you can do in SPSS that, I don't know how to do them all, and sometimes it's just, I gotta look up help and figure it out on my own how to do it. Yeah.
Yeah.
All right, so the steps for statistical significant testing, besides figuring out what's your hypothesis, what kind of data do you have? Are they independent? Is figuring out what your p-value is. So are you testing the significance at the 0.05 level? You know, have your null hypothesis, run the test. Then based on your p-value, do you reject it? Or do you fail to reject the null hypothesis? So if your p-value is 0.05 or less, You reject the null hypothesis, and there usually is a significant association between whatever you're looking at. If it's 0.05 and above, then your model isn't generalizable to the public. There isn't a significant relationship there that can be generalized. And yeah, then interpret your results. Okay. So errors. I don't know how much you've heard about type 1 error and type 2 error. I like my little picture that's on my door in my office. Type 1 is your false positive. So in the picture, the guy is being told he's pregnant. Clearly, that's not true. So it's, when there is no difference in the population, even though the results show that there are. So the results are showing, sir, that you are pregnant, but clearly he is not pregnant. And type 2 error is the false negative. So you're not pregnant, I'm sorry, even though clearly she is very pregnant. And there are ways to avoid each of those type 1, type 2 errors. So in some cases, one can be more serious than other, especially when you're dealing with medical conditions. If you do have, say, cancer, you don't want to be told that you don't have cancer. So you really would maybe want to try to minimize your type 2 error in that situation. No. I can never remember what they are except for the pictures. Okay. All right. Let's see. Just looking at the time and wondering if we want to start getting into these statistical tests, or did you guys want to start, take a break before we pull up SPSS and start doing things?
We can start doing things.
Start doing things? Okay. All right, so some statistical tests, that we're gonna be looking at are the chi-squared, which is for nominal data or nominal and ordinal data. So the chi-square is something that we're gonna find under the crosstab analysis that we've been doing. T-tests are scale data, so basically numerical data. So the example of height between men and women, you would do a t-test to see if there is a difference between the mean height of men versus women. A ANOVA test, that's done when you have multiple categories. So how about race and height? Do races have different average heights? So there's more than 2 races out there. And so ANOVA, you would put race in there, which could be, say 5 races you decided to use. And then you would look at the means of those 5 races and do the mean height differ among those 5 races. So the chi-square is when you have 2 options. The ANOVA is when you have multiple categories, 3 or more. And then the regression, we have the F-test and T-test. And just basic linear regression, you'll get an F-test when you do the linear regression. And linear regression is obviously for 2 numerical points. Okay, so that's kind of a quick summary sheet of what the tests are that you guys are going to do. Okay, so here's just kind of a picture of it. And so here's an example, with the cross tabs and an ANOVA test. So we were talking about you have different categories here, and do the means of say A, B, and C, do they differ among each other? So say this is height of 3 different races. Does the mean height for each of these races differ? That would be kind of your ANOVA test. Down here is an example of contingency tables. So again, if we had different groups, you look at does the response kind of fall into different buckets here, basically is what this is doing. So does group A tend to say, response of maybe yes more than no, or does group B tend to say, no more than yes, something like that. Linear regression, we've run through that. We're not going to get into ANCOVA, that's past this class. And then logistic regression. That's where you have a predictor and it's a yes or no event. Do they go to jail? Do they not go to jail? Do you kill a moose? Do you not kill a moose? You know, one or the other. Okay. And so, here's another little cheat sheet, and yeah, that's the one I handed out in class, just to give you a refresher as far as, okay, if you have nominal data, more than likely you're gonna be doing lambda for your measure of association, and you're gonna be doing a chi-square. Ordinal data, more than likely you're gonna do the gamma, and your statistical inferential statistic will be chi-square. And then for interval or ratio data, we had the Pearson's R, and you'll do a ANOVA or independent sample t-test. We'll focus on the ANOVA today. Okay. And it can get very complicated. So this is just, you know, for your reference, there are Kirk's-Wallace, Mann-Whitney, there are many different tests out there, so we'll ignore that. And focus on the ones that you're most commonly gonna come across. So the chi-square is basically when you're looking at the frequencies, is what you observed in your sample different from what you expect? So imagine if you had 4 boxes and your assumption is that your samples would be evenly distributed within the boxes. And it might be sexes on one side and I don't know, support for Hillary Clinton is on the bottom. You know, you have like sex support, yes or no. You would expect, say, if you sampled 100, 25 to be in each box. But the outcome, what you get, might be something very different. So this tests for whether what you see is different from what you expect. In this case, it's randomness, an equal distribution. Okay, and so this is just kind of an example of maybe this is what you expect to see, and this is what you actually observed with your data. So is this observation different from what you expected? In this case, it looks like probably. And so your test would be significant. Okay. So, all right, let's, we're gonna start to use SPSS here. And I think, you know, we're gonna look at happiness is not associated with the support of marijuana legalization. So that's kind of your null hypothesis. That there's no relationship between happiness and the support of marijuana legalization. So let's fire up your SPSS. And use the same data that we used last week, which was that new one that I gave you that has the recoded columns in it.
The one that says use me, right?
Use me, yeah, the one that says use me. Will, were you able to find the use me one?
I have not looked for it.
Yeah, I think it was under last week's folder.
Mhm.
Let's see, first content.
Okay, yeah, I found it.
Okay, I added in a whole bunch of like reclassified variables in there, so that's why I didn't want to waste time going through all that reclass. So it should be the GSS 2018_JS. We want to open that one. Okay. So there's a variable in there called happy. And what's the other one? Let's see. Happy and grass. So we're interested in whether happiness is related to your support of marijuana legalization. So we're gonna do a crosstabs. So, but this time, we're gonna do, you know, our test of association. Because happy, I think, has 3 levels to it. So ordinal, there's degrees of happiness. That's why we do that one. And then we're gonna check this chi-square box. So you'll put grass in the dependent row column, and you'll put happy in the independent column, grass in rows, happy in the columns. and then click on statistics. And then also don't forget to go to cell display so that you have your observed and your column shown. I'll do this quick, grass and happy. So analyze, descriptive statistics, crosstabs. Grass. Happy. Statistics, chi-square, and my association test will be gamma. Okay. Cells. I want to make sure I get my column percentages. Okay. Continue, and then hit OK. Alrighty. So what is this? What are our results telling us? Is it kind of hard to see from this table what's going on?
I think, American people who think it should be legalized are more happy typically,
I would say I would agree. I mean, you look under the people who are crabby, not happy, and, you know, the people who aren't happy, a lot of them say it should be legalized. Maybe they're crabby because they're not smoking pot. They think it should be legalized. Maybe they're in states where it's not legal. And then when you look at pretty happy, again, I mean, it's still among pretty happy people, there's high support for legalization. And then when it comes to, you know, very happy people, you know, they could take it or leave it, but still, you know, overall, there's more support for legalization of marijuana. So really crabby people, yes, make marijuana legal. Okay? And so is the, let's look at, our other tests. So the one test was the measure of association. So is the measure of association significant, or I guess, is the measure of association strong, weak, and what's the direction?
So it looks like it has a negative association and
Yeah.
it's moderate,
Moderate?
negative 0.2.
So yeah, negative 0.2 was moderate. See, do I have that in here? Yes, so when we look at, you know, our gamma and lambda and gamma, 0.1 to 0.29 is moderate and worth noting. So you are correct. And so when we look at this, yes, moderate, and it's negative. And what that means is, let's see, because the values are kind of weird, we gotta remember we have 1s and 2s there. So for me, it might be helpful to draw it out. So when we draw it out, we have our dependent variable on the bottom, and our dependent variable was what?
Dependent is whether or not you support legalization of marijuana.
Sorry, so that's up here, so dependent, so what is our, not legal was scored a 2. So not legal is a 2, a 1 was legal. And then, sorry, our independent variable is happiness. And so 1 was very happy. 2 was pretty happy, and 3 was crabby. Okay, and so since it's negative, the relationship is gonna go this way. So basically, as you move, from happy down to crabby, the support gets greater. Okay? I don't know, yeah, can you guys see that online or no, not really?
I can see most of it.
The drawing on the board, no.
No?
Well, it maybe if
I think.
I
the
mean,
key-
yeah, it looks pretty much like it did my ed. My smiley faces didn't have noses, but
Okay. All right, and, and one of the things, when you guys are thinking about presenting your results in your capstones, I don't know, I like to see things. Looking at tables like that, it's really hard for me to visualize what the heck's going on. So let's make a bar chart. So let's go up to graphs and let's go to bar. And why don't we do, stacked? Okay, and then we'll hit define. Okay, so I want our category access to be the smiley sad faces, so happy. Okay, and I want the defined stacks to be legal or not legal. So grass. Okay, and what we're gonna do is we're gonna look at the number of cases for now. Okay, and so I'm just gonna hit okay. Okay, so to me, the graph is much easier to read. I can say, oh, well, the most respondents were pretty happy, most people were pretty happy. And I can definitely see that the legal is much larger part of this in the pretty happy and the not too happy. This looks more evenly split. So to me, I can see what's going on much easier than the table. I like figures. So that's how you would do kind of this bar graph. The reason why I like this one over the percentage one is I can also get an idea of sample size with this one. I can see we have, nearly 800 responses for pretty happy. If I go and I change this to a percentage, I have no information about what the sample size is. I can see that, okay, around 42% of people who are very happy say legalize. And, this one looks like, yeah, it's near 70. So maybe I can see those percentages a little bit better, but there's no information on sample size. Where did it go? If you guys want to change this, right click your graph and go to edit. And then it's this little symbol up here that you click on, just kind of toggle back and forth between, do I look at the count or do I look at the percentage? I like the count. Okay, so this is an example of a chi-square, and we also did the measures of association. Okay. So, we've been going for a while. I want to kind of partially take a break, but also you guys can have some fun. And why don't you come up with some tests like we did last week? So come up with some tests that would require doing a chi-square. I'll go back to our chart here. That involve doing a chi-square, and let's see what relationships you guys do. I want the appropriate measure of association, and I want the appropriate inferential statistic. And let's give you a little over maybe 10-minute break, so we'll come back at 5:52. So 6:55, okay?
Okay.
I love seeing what you guys come up with. Expect great things from your analysis.
There's a variable that's labeled pig.
Pig?
And it's called pig and it's labeled pig.
There's no information as far as what it means? Huh. Pig. Okay. Let's see.
Pig B4 is also just a pig.
See if this has pig in it. Pig, okay, pig, probably maybe you own a pig, own a goat. Pig before goat, yeah. See if there's better information here.
Well, I think that was kind of funny, because I'm scrolling through all the labels and then I just see pig.
Does not have, has no answer. Okay, and they asked it in 2018. They went on a animal expedition, it looks like in 2018. Pet play.
That one's like, how often did you play with your pet last week?
How often do you seek comfort in your pet? No, they don't have my pet on there. I have ferrets. Which are, I think, illegal in California.
Is there a way to remove the inapplicable? Because I'm like getting it to show up on
Yes. Yes. We'll see, we'll walk through it and see. Yeah. There are places to define your variables, so we could not have it be defined.
That's just, oh, so you have to click one and double click, so I'm just. That's all there now.
People need more time to go, do their analysis. I think you're still, you good? Okay. Okay. So we have it online. All right, so, yeah, let's get started back up. I need to make sure I'm sharing my screen if I'm not. Let's see, am I sharing my screen? Hello, can you see my screen?
Yes.
Okay, okay, cool. All right, David had asked this question of like the scatter plot matrices. I guess in my mind, I was envisioning kind of what R can do, which, R is the program that we had kind of tried, but you've got to do, you know, some coding to do it. And this is kind of what I envision, like with a scatter plot matrix. So in this example, they're looking at different measurements of flower parts. And, you know, sepal length is on this side, and so this is relating sepal length versus width, sepal length versus petal length, sepal length versus petal width down here. So, you know, something like this, and, you know, obviously the bottom half is just repeating the top half, so in R you could cut these out. And then, you know, imagine you had different types of flowers you were looking at, you could color them by the different types of flowers, which is pretty powerful. And then you could combine your scores, your correlation scores with a graph and make something like this. So this would be, you know, the R related between sepal length and petal length, the R between the length and the petal width. So that's something you can do in R. The closest thing that I found in SPSS is you can get this correlation matrix. So I can get what my Pearson's correlation is among these various factors: income, height, email hours per week. So in this example, the email hours per week and other Protestant denominations, I have no idea what this is. You know, there is a weak correlation between that. And I believe to do that, I went analyze, correlate, bivariate, and I threw them all in there. And that'll give you this correlation matrix to explore if your variables are correlated. So if they are correlated, then you've got to start throwing some of these out and seeing which ones you want to keep. So does that help, David? California, David?
Sorry, I was looking at data.
This is the correlation matrix that you would do if you had a lot of variables that were going into your model and you wanted to determine if there was some collinearity happening. You're on mute. Okay. All right. So let's see, now I hear you.
Okay, sorry. So that value that it gives for the Pearson correlation in each of those, I see that that's like the cross-reference table, but is that the same, the value that's represented by that capital T? In the, like if you run the crosstab?
If we run the crosstabs and we check to do the Pearson's correlation, this value should come up in the crosstabs.
Okay, so this is like a crosstab of crosstabs, or it's like a multi-crosstab.
Yes, yep.
Cool.
So you don't have to do them all individually. You can look at all the interactions possible, combinations of variables. Okay, all right, so let's go around and see what statistical tests people chose to do. So let's start with David in the classroom. What did you do?
I stuck with the happy one, and then, the other variable is, health one, which
Okay.
is, people ranking their general health.
Okay, so you went to analyze and then did you go down to descriptive statistics?
Yeah,
Crosstabs, okay.
and rows health one.
Health one, okay. Where is health? There it is, okay. All right, so what was your hypothesis?
My hypothesis was the healthier you are, more healthy you are, more happy you are.
Okay, so health is gonna be determining happiness, right?
Yeah.
Okay. Let's see. Health equals happy. Okay, so the dependent is,
Dependent is the happy.
yep. All right, and this is the independent. Okay, and I always have to go back to my little PowerPoint and see which goes where, because, you know, I can never remember. So let's go to the PowerPoint and see. So the dependent variable, the row should be happy. And the column should actually be this. Because you kind of switched them up a bit. You switched up the dependent and independent.
Okay, yeah, okay.
That's fine. I mean, that's fine. That's the test you want to do.
Oh,
So I'm gonna drag happy up here and healthy down here. Okay? And then for your statistical test, what did you choose?
Same one, chi-square, gamma.
Okay. All right. All right, so tell us what the results are. Wow.
Pretty significant. I think the value was, yeah, 0.3, yeah, 0.383.
Mhm.
Yeah, pretty significant that health is directly health equals happiness.
Yes, is there a direction to this?
Yeah, it's going well. Yeah, for sure. Yeah.
Yes, and so the numbers are, as you go increase in numbers, you increase in numbers here. So as you get higher up, you get poor. As you go higher up here, you get not too happy. So the poorer your health, the less happy you are. And you know, the reverse, the higher your health, the happier you are. Yes, definitely, there is a relationship there. Did you do any charts?
I did, but it's actually, the results are pretty different from just switching the variables around.
Yeah,
Yeah, hold on, let me try it again.
it's always important to figure out, your dependent and independent variables.
Yeah. I did a bar graph.
Simple or the stacked?
The bottom one.
Yeah.
Cluster stack.
We'll probably drag happy down here. Remove grass, away, happy down here, and then health.
And then, if you change it to percentage,
Okay. Well, I'm very happy that the people who are, the poor health is a very low percentage of our overall sample. That's a good thing to see. I like that. Okay, and then you changed it to percentage. Huh. Definitely a very clear trend there. Yeah, okay. Good job. So yeah, that's exactly how you would do that test. Okay, all right, Alil, what did you do?
So I did. Let's see here. So I'm trying to like open it up. Okay, so I did that your confidence in the press, or that there's a, yeah, confidence in the press indicates whether or not you are depressed. Oh, that rhymes. I I did not say that out loud till just now.
Okay, so confidence in depressed will actually indicate your level of depression. So your dependent and independent variable are?
So I kind of had trouble with this, because I wanted to run it as like the independent as the depressed,
Okay,
and then dependent as compress.
okay. So I would probably phrase it a little bit differently. So let me see, you want depression to be your independent, so, does, is confidence in the press related to depression? So is confidence in the press related to depression? And the idea is that if you're less confident in the, press, you're probably maybe more depressed. Like that?
I would think
Or
like
you
more
want it to
confident
be
in the
in your-
press. Yeah, more confident in the press, less depressed. Wait, yes. Yeah.
Because the other way to look at it is, if you're depressed, are you less confident in the press?
Yes.
Is that what you want?
Yes.
Okay. So for that, it'd be like depression would be your independent. And your confidence would be your dependent. So you would be saying, depression is related to how confident you are in the press. And maybe you have a direction to it saying, more depressed you are, the less confident you are in the newspapers. Okay. So going back to our little thing, the dependent variable would be depression. So we have depression in the rows. And our independent variable is confidence in the columns. Okay, all right. I always have to write things out. That's just the way I work. Maps and writing things out. All right. Back here, SPSS. All right, so you did a crosstabs?
Yes.
All right, crosstabs. All right, we said the columns is gonna be, confident in press. What is that, variable?
It's compress.
Compress. All right. And then, depression,
Is depressed.
press. Okay. All right, and what statistics did you choose?
I chose gamma.
Okay. Your chi-square, yep, okay, so let's take a look and see if this is true. All right, so what did you find?
I found that there was a negative direction, and so 0.044. I don't remember. Is it 0.03 or is it 0.3? That's like the cutoff.
Well, for the measures of association,
Mhm.
that is the one where we look from 0.01 to 0.09 is weak. So basically, if it's less than 0.1, it's weak.
Yes.
So it's weak.
Mhm.
Okay, so there's a weak, weak association, and it's slightly negative, meaning that as, your confidence decreases in the press, you're actually kind of less likely to be told you have depression. Or sorry, the opposite, it's a negative. So as, your confidence in the press decreases, you're more likely to have depression, but it's a very weak correlation.
Okay.
And is your statistical test significant? Chi-square test, is that significant?
Is it no?
Is 0.07. 0.07 is above the threshold of 0.05, so no, it is not significant.
Okay.
So that means that there's really no relationship. That means that you can't generalize it to the public. So if we go back to our chart here. It's a go back to the drawing board scenario. Okay, so little help in predicting, not really generalizable. I would have thought maybe there would have been more of a relationship, but the data says, So,
Yeah, I would have thought so too.
cool, good job, I like that. All right, so Claudia, what did you do?
So I did, the variable is called homosex, but it's like to what degree
Homo or homo?
homosex. But
Okay.
it's, to what degree do you disagree? Do you think, to what degree do you think having homosexual sex is wrong?
Okay, all right, so, homo sex, let's say, right? Okay, wrong, okay, and what's your other variable?
Did you vote for Clinton or Trump?
Clinton or Trump, okay, all right. Trump, oh my God, okay, so what's kind of your independent?
So for independent, I did the homosex.
This is independent, okay,
Yeah, because I thought your views on this are gonna influence who you vote for.
okay. So you think your status as far as your opinion towards homosexuality will influence your vote? Okay, all right, so the independent is the column, so this one will be column. And this one will be row, okay, all right. I didn't even know that was in there, all right, let's see. This has gotta be significant, man. Something's wrong with the data, if it's not. All right, so, probably homo it starts with,
Yeah, it's literally homo starts.
okay. Okay, hey, there's a 1 too, so column, okay, and then vote,
Then it's on press 16.
press 16, okay. Okay. All right, and the statistics. What did you choose?
So I did chi-squared and gamma.
Gamma, okay, all right, because I think there's probably directionality to these, okay. Let's see, oh my goodness. Wow. Oh, I see what you mean, there's don't know and no answer. Huh, okay. Okay. All right. Looking at this. Okay, so you want to try to remove these.
The 0, 8, and 9, because they're inapplicable to the data.
Yeah, inapplicable, okay. Okay, let me see if I can remember how to do this. Let's go look at our data and see if those are flagged as no data. So, this appears to be an issue on the press 16. So let's go look at press 16 here.
So I have that as missing and it says none.
Press 16. Okay, so it has these labels, okay,
But you see like right next to it are the ones that are missing.
none. Okay, so here you need to put the discrete missing values, and I believe it was 0,
Yeah.
was it 98
No, 0, 8, and 9.
and 9? Okay, so I'm gonna put those in there. I'm gonna tell it this, these are the missing values, okay? All right, so we have that. And then I'm gonna go back to our thing here and just close this one out, don't save. And then let's try to rerun that. Here you go. Move on.
Okay, yeah.
Okay, so that was an excellent example of where they didn't properly code their data. So, if you're having the problem that Claudia had, where it's including the I don't know and just bogus responses that you don't want to include, always go back and check your data in the variable view and go to this column called missing and make sure your missing is defined. Okay? I've had students turn in homework assignments where they do the bar graphs and stuff and they include those columns that they shouldn't include those categories. Okay, so getting back to this, now that we got the appropriate data, what is it telling us?
Well, what helped me was looking at the graph because the chart's a little hard to read.
Okay. So you did a bar graph?
Yes.
Plus
Although now that we took out
all the other
the
stuff.
missing things, it's very clear, like if you look at the 1 always wrong,
Yeah,
most of those people said Trump
yeah.
by far and away.
Mhm.
Then if you look at 4, not wrong at all, it's like you flipped it and now most of those people are saying Clinton.
Yep, yep. So your measure of association. It's large, right? Strong, very strong. It's negative in the fact that, you know, Trump is 2. And so always wrong is 1, so that's why it's an inverse relationship. Yep. And then your chi-square test indicates that it is significant, so this would be generalizable to the public. So it's an important predictor and it's generalizable to the public. Okay, Does that make sense to everyone? Yeah, it's like, we figured that was gonna happen. All right. David, what do you have for us? California David.
So I've tried a bunch of them trying to get the result, and I haven't gotten the result I wanted, unfortunately.
You're data mining.
Yeah, you could argue that. So should we just take we can just take one. So I was looking at zodiac sign as the independent variable, and I ran a bunch of crosstabs with different dependent variables. And I wasn't able to get anything that both had any kind of correlation with significance. I did get a strong correlation on one, but it had no significance. So we could run one, but it's not gonna be fun.
Okay, my thinking on that is how many different zodiac signs are there?
12.
That's probably why you're not getting a statistically significant result, is your
Mhm.
power is so reduced because you have 12 categories.
Yeah, because everyone's spread out across. And like the thing, yeah, if you get one that has, I mean, I can get results with significance, but if they have significance, then they don't have interesting correlations.
Interesting, okay. Yeah, that's
I
the
mean,
problem when you have so many variables, so many categories, why collapsing them down sometimes helps make your analysis a little bit more clear. You could be like,
yeah.
signs in the spring, signs in the fall, you could do it by seasons or something like that.
I mean, I think it would make more sense to like collapse them into like the elements, like the fire signs and the air signs and the water signs. But yeah, we could try some different things.
Too bad they don't have that, what is that, Myers-Briggs test or something, where we could have the
Yeah,
Myers-Briggs
that would actually be interesting. Yeah.
Yep, okay. All right, so I think you guys got the chi-square test covered. Great job. All of you did wonderful on that. And we covered making the bar charts and stuff like that. So t-test.
Actually, can I ask a question about the interpreting the results I was getting? So I was running both gamma and lambda tests because I wasn't generally what was happening is I was looking at a combination of ordinal and nominal information, right? Because zodiac signs, in the way that I'm thinking about them as nominal. Like you could say that they're ordinal if you're looking at them as like when were you born, but like that's not really how I was considering them. So lambdas in the chi-squared result, I'm probably going to get these backwards, but I'll just go for it. Lambda says ordinal by ordinal, like that's like subtitle, and gamma says nominal by nominal. But do you have to use a different one if it's ordinal by nominal, or vice versa?
That's a good question, and that's kind of where you get into, yeah, what do I use? I would ask yourself, does it make sense for your measure of association to have a direction? If it doesn't make sense for your measure of association to have a negative or positive associated with it, then you should probably use lambda.
Okay. Yeah, that makes sense.
So in that case, I mean, you have all of these different zodiac signs, and I mean, it doesn't really make sense to say as you increase in your zodiac number, whatever they assign, you have an increase of happiness. I would say more you would use probably the lambda, because it's just saying that there is, some association between zodiac sign and say happiness. Okay.
Okay, right. Thank you.
Yep. All right, so t-test. So let's do a t-test. How about our hypothesis is men spend more hours watching TV than women? So what would be the null?
There's no relationship between gender and hours spent on TV.
Yeah, they spend an equal amount of time watching TV. And so, what's our independent and dependent?
Independent would be gender.
Yep. And then your dependent would be TV hours. And we're doing a t-test because the TV hours is a numerical. It's a number. And so we can look at the difference in the mean hours that men spend and the mean hours that women spend. So, this is, numerical, it could be scale, if they rounded it, we'll say this is scale and this is nominal, okay. All right, so, we go back to here and, we're doing t-tests. We're gonna do the Pearson's R for our measures of association. Okay, and so, our dependent is gonna be TV hours and our independent is gonna be sex. So what you wanna do is you wanna go to compare means and proportions. And go to means. Okay. Once you got that, then we're looking at our results here. Do men spend more time watching TV? More hours?
Hopefully, no.
No, it looks like women spend 3.01 hours watching TV. And men spend 2.8.
Yeah, my hesitancy is we haven't done
We haven't done the statistical test, but just on the means, this is what the means say. The mean is telling us females are actually watching. So now let's do some tests. So we go to the compare means and proportions and independent sample t-test. Line up here.
So, in this one, what are test and grouping? Are those analogous to dependent and independent?
Yeah, so the grouping variable is gonna be your sex. And your test variable is gonna be hours.
It-
And, it's a good idea to click this define groups and define your groups as basically group 1, which is males, and group 2 is females. Okay. All right, and then, you should hit continue and then, okay. Let me, do it on my end. Define groups. Group 1, group 2, okay. All right, hit okay. All right. Let's see. Okay. Looking at the results here. Okay. So with this, it's only giving us, the results from the statistical tests, so we're not doing any of the tests of association. I don't see like a Pearson's R here at all, so we would have to do that separately. Pull this up. All right, so here's kind of the annotated results. So this kind of Levine's test here. It indicates that, the variances are equal between the two groups. So none of these really is significant. If these were significant, it would indicate that there's unequal variances happening here. So we're fine with the tests that we've done. So that's okay. And then we take a look, this is kind of a little weird way to interpret it. But let me see. All right, so in this example, what this means is like, out of 1,000 samples, we would expect 269 of them to show men watch TV at least 0.16 hours fewer than females. That's what that means. And because the difference in the mean here you see is 0.16. So the difference between men and women is men on average watch 0.16 hours less than women. And because it's statistically significant at this level, if you had 1,000 samples, 269 would show that men watch fewer TV, approximately that many fewer hours. So that's what that means. Looking at this, the significance is greater than 0.05. So I would say that there's no real significant relationship between the two. So I would say it's not really statistically significant that there's a difference between men and women and how much TV they watch. That's not a huge difference at all. Okay. If we wanted to do the measure of association, how would we do that? What's the appropriate measure of association?
I think you said Pearson's R.
Pearson's R, right? And I think we got that doing this linear regression, if I recall correctly. Let's see, we're doing sex. And we're doing that. Let me think about this. I have to go back to my stuff here. Thinking. Solutions are, okay. I'm trying to remember where exactly it was. I think it was like under regression. You guys remember where it was? Should remember, but
I think you get it in the crosstabs. I just ran the linear regression and I didn't open the options. I don't think I see it.
crosstabs, okay.
But I think you go into the options in the crosstabs before you run it, like that's statistics, and I think you can choose that.
I think you can click correlations here. So we'll click correlations. Off R squares, okay. And so gender. Sex. Okay, we get a Pearson's R here. Of 0.028, so definitely not a big relationship there. So that confirms what we saw from our other result. From doing our t-test.
Okay,
no-
so in this table though, sorry to cut in, but real quick. So, but if you go over two values, approximate capital T,
Mhm.
what is that value representing, or is that something that I don't have to know?
It's something you don't have to know.
Awesome. Okay, that was confusing me.
Yeah, based on a normal approximation, based on asymptotic. Yeah, you basically just have to focus on this value here. Yeah.
Okay.
Okay. All right, so. Save, okay. All right, so that was a t-test that we did. And so, I mean, to kind of make it more confusing, but we weren't gonna go into it, is sometimes you can do one-sided and two-sided t-tests. So say you just were interested in does TV hours differ? Either way, who cares if men do it more, who cares if women do it more? That would kind of be your two-sided t-test. But maybe you just specifically wanted to test, do men watch more TV than women? And you're only interested in that direction of the test. Then you would do something called a one-sided test. You can break these tests down to be even more specific if you're just interested in answering a certain direction. We're not gonna get into that kind of fine details, but it is possible. Okay, so analysis of variance, ANOVA, this is a big one. ANOVAs are used a lot, and ANOVAs are pretty robust, even, even to some of the assumptions. If you don't quite meet the assumptions, lots of times you can still get away with ANOVAs. And the ANOVAs, are testing, is there a difference in the mean among groups? So, lots of times people can display it as like these little box plots with the error bars. And then lots of people will put little asterisks to kind of show, if there are differences in the means. Like in this example, I would say there's no difference in the mean between A and B, but C is significantly different from A and B. If I was to run statistical tests, I bet you that's what it'd say. So you probably have a little asterisk here above the C and say that. Okay, so ANOVAs. Okay, it's looking at the variance. In ANOVAs, you can look at the variance within groups. And you can look at the variance between groups. The one example that I was just looking at, we were kind of looking at the difference between the mean values of, say, A, B, and C. When you run ANOVAs, sometimes there's the ability to look at, is the variance and the significance of your model coming between these differences here? But how much of it is also associated to the variance within each population group? Yeah. So it's a little bit of a fine scale matter, but you could say, I'm just trying to think of an example here. If you were looking at, like, say, income again from different working classes. You could be like, well, our model is being driven by the difference in the income between the classes. What is the mean income? However, a large portion of the model is also being driven by the huge variability, let's say, in the poor class. Maybe your poor class has a lot of people who just, poor working, make a lot of money, but they're still classified as poor working. Who knows why? So maybe that category has a lot of variability, and that can be really playing with your model and contributing a lot to your results. So that would be an example of where you looked at the variability within income within the classes, and what is that doing? Versus looking at the variability between the mean of, working class, middle class, upper class. But let's do an example. So let's examine the relationship between religion and education. So, we're interested in whether different religious groups have different levels of education. So our dependent variable is going to be education, the years of education. And our independent is going to be religion. So we think that different religions will have different amounts of schooling. All right. And your education in years, that's a number variable. And your independent religion is a categories, nominal. All right. So let's go the general linear model and go to univariate. We only have one parameter, religion. All right. And so fixed factors, put in religion, and your dependent variable is going to be education. Then go to options and click descriptive statistics and homogeneity test.
¿Me puedes dar otro, regalar otro queso?
Okay. So we're basically looking at whether kind of a categorical variable is influencing a numeric variable with our ANOVAs. Okay, and then click next. What do you guys get? Go and do mine. Religion. Each I. And we get education. Okay. I'm actually doing it in a different section than you guys are. Let me see what this results in. Okay.
Hmm.
How does that compare to the results you guys got?
Stay.
It's the same? Okay. So it doesn't give me as much information. It gives me the model results. I don't have the option to check for, variance, equality and variance. And it's just giving me the counts, it looks like, of the number of religious preferences. So did you guys do, which one did you do? Go back to it. There's multiple ways to do this in this program. So general linear model, I think that's what I did. Isn't that what I did? I'm just playing around right now, sorry.
So I think I'm getting a result that looks the same as yours. If that's answering your question, I don't understand the difference between the way you ran it though.
This, and then there's this way to run it. I'm just wondering, did you guys get the options? That I got when you go to univariate? Univariate options, did you see that?
Yeah,
Okay,
if you follow that, it looks like the
Options.
presentation.
why don't you show? Uh-oh. See. You might have to close this, it's not acting proper.
The options that I get are to like include different different things in the view, like descriptive statistics.
Okay.
And something called heteroscedasticity test.
Yeah, heteroscedasticity, that's what we wanna do. My computer is not behaving because it won't let me click on anything. Let's see. Let's see, what's that called? Wow. Let me see. I'm just gonna kill the program because it's not behaving on me. All right, die.
Do you want me to screen share while you're getting that going, or is it? Oh, it'll probably be fast.
I can get it back
Me,
up.
when I have to kill SPSS and start again, it's like it's a whole thing.
Die. No, don't send. You're not gonna do anything anyway. All right.
You never know, they might run some statistics on it.
Yeah.
They're gonna ask, do people in Alaska get more errors?
Do they have less patience? All right, here we go. So analyze general here, univariate. All right, let's see, we're asking religion. All right, and then education. Okay. All right, and then we looked at options. And that's what's killing my program. It's a bug in their system. I can't go to options. So I will not go to options trying to VPN in because that is killing the program. You bring it up, David. Can you bring it up, David, or no?
I'm sorry, can I bring up?
The result. Or a little. Yeah, how about we'll have a little. A little, can you share your screen and bring it up?
Oh, sure, if she can, that's cool, but I can do that too. Sorry, I didn't hear that.
She stumbled upon something cool.
Sorry, am I bringing it up or not?
Yes, let's have a little bring it up.
Okay. Oh, no, David brought it up.
It's okay. Yeah, a little, why don't you bring it up? And that way you can show us what you stumbled upon.
Okay.
Cause yeah, there's lots of things that can be done in this program. It's just playing around with it. Okay,
What screen am I sharing? Oh, okay.
yeah. Okay. So
Uh,
which religion had the highest education, the most years?
Um, so I wasn't sure how to read this.
Let's scroll back up to that chart that's kind of cut off, that descriptive statistics.
Mhm.
Okay. So in that chart, that tells us the mean number of years that each of the religions goes to school. So which ones go to school for a pretty long time? In the descriptive statistics.
Oh, looks like, yeah, Jewish? No.
Yep, Jewish and Hinduism.
Yeah.
Yep. And Orthodox Christian, all of those are gonna have values of 16 or above.
Mhm.
We're the ones that go to the least amount of school. Native
Is-
American, other Eastern,
Mhm.
uh-huh. Okay, all right. And then, okay, we have the Levine's test of equality for variance. And so remember, if this test is significant, your variances are not equal. So this test is not significant, so that means you have no problem doing a parametric test and the variance is equal. So you're good. You want to see that be not significant. So yeah, you look at that last column called sig. Yes, right there. Yep. All right, and so what does our model say? Does our model say that there's a significant relationship between your religion and the amount of schooling you do? So with that bottom test between subject effects and that last column, it says that it is significant, highly significant, less than 0.001 is your p-value. So, and that religion column, that is less than 0.001. So yes, it's definitely significant differences among the amount of school that's done with the religions. So that's how you'd interpret that.
Dang.
Does that make sense? David is laughing.
I was laughing about something unrelated. I wasn't laughing about this. This is actually really interesting. And I do want to totally clarify, although I do understand this. There's this funny double negative thing here. So when we're looking at the Levine's test, the significance, it's not significant because the value in the significance thing is too high, but that means that it is parametric because this test is not significant. So a really low significance figure is what we're going for.
But if you have a really low significance figure, you have a problem. So your variances are not equal.
Oh, in the Levine's test, yeah, no, but like in the other ones, the low significance, is what we're looking for. In these, so in these tables we're looking at, in the first table, it's the first value. No, those aren't actually values. Where in here are like the there's no like I guess in this case it would be lambda. No, in this case it would be gamma. There's no gamma values here, right? That's not something we're seeing. We can just visually see that the numbers for certain categories are a lot higher, or does one of these numbers represent like the correlation?
Well, in this one, none of these represent the measure of association. We would need to have to go and do the Pearson's R.
Okay, so is it
So-
possible to get like a significant, is it possible to get a number that shows significance but without, we did talk about that. Yeah, you can have like you can have a very low significance without having a meaningful measure of measure of what's it called?
Association?
Correlation. Association, right?
Yeah.
Like these significance figures in their own aren't definitive in that way.
No, I mean, what this means is because the statistical inference test is significant, this result is generalizable to the population. And if you wanted to look at how strong that association is between religion and education, that's where we would, in this case, do the Pearson's R. So, if you want to go up to analyze.
And is the
And,
Pearson's R, is that like a third option to the gamma lambda
yes.
divide? Okay.
So Pearson's R, go to descriptive statistics. Crosstabs. We want to remove that. So I think our columns are dependent, no, columns are independent, I think. And our independent is religion. And our row was education. Go to statistics. And uncheck chi-square, uncheck gamma, uncheck correlations. Okay, continue. Hit okay. All right, so scroll down to the bottom. All right, so our Pearson's R is 0.5. So in this case, our model is significant, so it's generalizable to the public. However, it's a very weak correlation. You know, it's a very weak association. The Pearson's R is rather low. And I think that's happening because we have so many different religion categories. Okay? And actually, if you scroll back up a little to the results from your model. Okay, you see where it says R squared is equal to 0.025. Really, the Pearson's R is the square root of that. So if we took the square root of 0.025, what would we get?
0.05.
Yeah, so that's kind of the backwards cheat way to get at what is your Pearson's R, is taking this R squared here and taking the square root of it. So you don't really have to run the other test, but we did it to show that it actually does make sense.
Where's the R squared? A little, if you see it, can you put the mouse on it? Okay, so it was in, we got it from the first like statistical run. So is that then like the measure of, I'm gonna butcher it again, but the measure of correlation
Yes, the
is
measure
like,
of correlation or
is implied
association.
in that. Measure of association is implied in that. Okay,
Mhm.
so why on this data are we using Pearson's R and not gamma?
Okay, can I take back the screen? Hello? We are doing that because, when we look at the suggested tests, we see that we're dealing with interval ratio data. Education is a number. And we're looking at the mean difference in education levels among the groups. So ANOVA for our inferential statistics and the Pearson's R for our association. We're not talking about counts here. This stuff is usually you're talking about counts. Here we're talking about mean values.
Okay, I understand what you're saying. You're not screen sharing.
Oh,
just
golly,
to
I'm
know.
sorry.
But no, but I understand it from what you said.
Here. We're dealing with the interval ratio, and so we're looking at the mean, we're looking at ANOVA, and we're gonna do the Pearson's R.
Okay, interval and ratio. I am having trouble understanding this because one of the pieces of data is still nominal because we're still talking about religious identification as a variable, right?
Yes. Yeah,
Okay.
so maybe it helps to kind of look, at this figure. So this, on this side would be education, the number of years. And then each of these histograms would be the different religions. So Hinduism and I think Buddhism would be up here. And then the Protestant would be like in the middle. And then there was the other Eastern that was pretty low. So we are looking at the distribution of the number of years of education among the different religion classes. So we could make a graph that looks like this, the average religion, for the different types of religion groups, the average number of education.
Okay, but yeah, I get it. We're not, it's still nominal data, but we're not running the normal nominal data test because we're looking at averages across the groups.
We're not looking at counts.
Because we're not looking at counts, yeah.
Yeah, we're not looking at how many said happy, how many said part of happy, how many said grumpy. Those are counts. We're actually looking at, a distribution of education.
And is there anything in these tests that can tell us about the direction of causality? I know we've talked about that in some instances, and like I know you need a hypothesis, but this one's interesting because I feel like you can kind of hypothesize either way. I don't know. I guess you could do a regression on like religion of parent or something and see if that's, I'm sure that's going to be the strongest predictor of religion.
Well, I mean, you're close in your question. in that you're not really probably gonna do, you know, a tail test where, I mean, if you group them into Eastern religions, say, do Eastern religions have higher education than Western religions? And say you wanted to test that specifically, if Eastern religions have higher education, then you would do a tail test. But the thing that maybe you're asking about is, you know, we have our result, and let me see if I pasted it in here. Let's see, that's something else. Let me see if I have, okay, we have a result, and this result is telling us that, yes, there is a significant difference. Religion, you know, say, is influencing education. What is it not telling us? It's not telling us which religions are different from each other. So it's not really telling us what's driving this. You know, is, you know, Jewish really different from Catholic? Is, you know, Hinduism and Jewish, is that a significant difference? It fails to tell you, looking at the pairwise means what is significant. And that could be important. You know, looking back at this thing that I told you, the pairwise means would tell you A is not different from B, but C is different from A and B. So your overall model result would say, yeah, there's a significant relationship, but you don't know exactly what. And so there is a way to do the means test within an ANOVA, so you can figure out what's driving your result. This one is hard because there's so many different religions. You know, when you have like 3 categories, it's a lot easier to do a means test. I did this with moose hunting and antler size. You know, trying to figure out, does, you know, guiding and use of a transporter affect how big your moose is that you harvest? And so we looked at the mean antler size of moose among people who used guides, among people who used transporters, and we actually looked within moose density, because the more densely populated your moose, the less healthy they are, and their antlers are gonna grow as big, they don't have as much food. So we did a test like this, and so we were able to say, okay, antler size is significantly different, say, between low and medium density populations, but not between high. So you could tease out among the populations, what's really driving your antler size. You know, I can't remember the exact results, but my guess would be the high has the lower moose antler size, and the low and medium probably for small little, you know, antlers. So
That's fascinating.
yeah, that's an example where you could use a test like this and figure out what's actually driving the difference in your means.
Sure.
So hopefully that's not too confusing. Okay, everyone's gonna go hunting now. All right, okay, so let's see. All right, why don't you guys try one? So before we had men and women watching TV. We didn't do an ANOVA because you only have 2. You have men and you have women. Let's look at political party. There's more than 2 political parties. So this is a case when you would use an ANOVA. We want to look at, does political party affect the number of hours you spend watching TV? So I want you guys to run this ANOVA and then let me know if it is significant. And I'd like you to also do the association test too.
So you can run the ANOVA through the linear regression, right?
Yeah,
And the association test is going to be a crosstab.
the
Correct.
association test would be a crosstab, yes, but remember you can kind of cheat and get at it with that R² score.
Okay.
Is party the same as party ID?
I think so.
Okay,
I think that's part of identification, right?
I don't know, let me see, we had that book up before, let me see if we can find what party and party ID are here, really quick. Party. Party ID is political affiliation, maybe it's supposed to be party ID, I left the party
Yeah,
Yeah, party ID, I'm sorry. I was just focused on party. Should be party ID, I guess.
Is one-tailed versus two-tailed significance gonna play into this? That's
No,
something-
'cause we're not
okay.
really trying to test specifically whether, say, Republicans watch more TV than all non-Republicans. We're just interested in, is there a difference in the mean number of TV hours?
Okay, so if I get a one-tailed significance result, that's the significance result.
Hmm. I'm not getting a one tail when I do it. Let me, or I did it before. Let me, explore here.
I might have done the options.
Okay, you
Or
might
I
have
might
played.
have selected my options poorly.
So weird that this thing doesn't like the VPN.
We're good. I got a different. I got a significance value. The way I set up the options, I got significance values returned in different places. The ANOVA significance value is I got that as well. So
Okay.
I'm happy.
All right, so based on your results, who spends more time watching TV? What the mean? Who has the highest mean?
I think it's strong Democrats.
Yeah,
strong
yeah.
Democrat.
It's, okay, it's interesting. Democrats spend more time. Overall, the total mean for our entire data set is 2.94. Yep. All right, is the relationship significant?
Yes, there's significance.
Very.
Yep. Yep, very significant, exactly. So our results are generalizable to the public. Is the measure of association, weak, moderate, or high?
Mm,
I need to bring up my little calculator here, so we wanna take, 0.015 and take the square root of that. So we get 0.122. That's basically our Pearson's R. Is that weak, moderate,
Pretty weak.
Weak,
pretty weak.
moderate.
weak to moderate, yeah, so. You know, it's significant, it's weak to moderate. I would probably say there's some confounding factors in here that are driving this result. So I wouldn't hang my hat on this, I would probably be looking for some other things to add to my model. Yeah. So, let me see, let me go back to this. Go to analyze. Okay. Why did you guys try to do the same analysis, but go to general linear model and go to multivariate? And so we'll throw in here party ID again. And we'll throw in TV hours. But let's pick something else that we think might be driving this. So what's another factor here that we want to throw in our model besides party ID?
Maybe. sex.
Hours worked.
Hours worked. Okay, let's throw in sex and hours worked. So let's find sex and hours worked. Hours worked. What's the code for hours worked, David?
I don't know, I'm still looking for it. I know it's in there though.
Okay. Looks like it's HRS1. Yep. Okay, let's see what this gives us. Well, let's do it. Okay, it won't let us, does it let you guys do it?
Nope.
No, okay. It's not working the way I want it to. All right, let me see if it wants it to do it this way. Try this. Dependent variables, TV hours. Try it this way. See, this is what happens when you do stuff on the fly. All right, our. Okay, sex was in there.
So
Wait,
if you-
is it because it wants things to go into covariates?
I'm not exactly sure what it's doing, if the multivariate, it can't be predicting too. I'm not sure. I'll see if this route works. Lil, were you gonna say something?
Yeah, so the tip I threw in the chat was like if you click on any one of those variables and then start typing what you're looking for, it'll like automatically highlight it.
Like over here, you start typing?
Yeah.
Okay, that's nice. Okay, well, it does allow us to do this, so I just ran the model. And it looks like it works if you do generalized and you just still do the univariate. And looking at the model, the results, I look here and it says the overall model is significant. So this model corrected is significant. Hours worked, is that significant? Yes. It's very significant. Is sex significant? No. No differences between sex, and that kind of agrees what we saw before with sex. All right, is party ID significant? Yeah, it's significant. A little less so than the hours worked, but it's still highly significant. What this is doing is it's also testing all the interactions. So if you looked at something that combined the hours worked and your sex, would it be significant? And it is, which to me says that there's probably a difference between hours worked between men and women. If we looked at that, I bet that would be important. And so if I was doing this modeling, I would drop out sex, because what's driving it, I think, is the hours worked. And I look at hours worked in party ID, that's interesting. That is significant. I would explore that relationship between hours worked and party ID to see if, there's something driving this significant interaction. But it's fine to leave it in the model, because it can make sense, whereas sex, we would take it out, because it's just on its own, it's not explaining anything. And then this is a three-way interaction where you look at all three of them, and whether in combination simultaneously, are they, predicting TV hours? And they are, but again, I think it's hours worked, and party ID that are driving this. The sex could be dropped out. So you always want to simplify your model, you can. So, yep, significant, and our measure of association is gonna be, 0.512, the square root of that. It's very, overall, the parameters within the model are highly associated with TV hours. But the problem is, we don't get the Pearson's R for each of those variables. So you would need to run it on your own, each of those specifically. You know, do the crosstabs and get your Pearson's R. But that's how you would do like a multiple regression. Okay?
So when you're looking at this and like we get the greater significance value for combining all three, is that like an artifact of combining all three? Because like that, looking at them separately, that doesn't really make sense. It looks like that, that yeah, sex is not actually that powerful of a driver. But then when you combine all three, you get that like even lower significance value. So is that like you like maybe just in this case, your gut feeling, is that something that you want to follow up on, or?
Well, I mean, what's driving this is your hours worked in your party ID. Because anytime you add in more parameters, you're probably gonna explain more of the model. You're throwing more junk into it. So if you're probably gonna try to explain more of the variance, the more you add to it. Yeah, maybe I explain a little bit here, a little bit there. So when we even look at this one that's called sex and hours worked, even though sex clearly is not important, it it is brought up by hours worked, which is highly significant. It brings this 0.1 value up to 0.028, but at the same time brings down this less than 0.01.
Right, totally. And same thing with sex and party ID, like you see the same thing there.
Yes.
Okay, so it's adding a little bit of explanatory power, which takes you from 0.001 to less than 0.001, but it's like probably not worth including in this case, right?
Exactly, yes. But I would definitely explore like this relationship between party ID and hours worked to see if there's something going on there. Because I mean, you're modeling it also, you have to tell a story and you have to explain why is this interaction significant? And you might have a bar graph that shows, that, well, it's significant because, I don't know, more liberal people spend, I think, more time watching TV. We saw the Democrats had the higher TV. So this is why it is the interaction between party ID and that, and you look at hours worked, maybe people who are more liberal don't work blue collar jobs or something and have jobs where they work less hours. So maybe there's something going on with that hours worked, being liberal and watching TV. I don't know. You have to tell a story with your statistical results and interpret it to your audience. Because you can come up with all crazy results of all sorts of significance, but doesn't make sense. And what are people who make decisions going to do with it? This is a policy course. Is it useful for making policy decisions? Yeah. Okay. All right, so, like last week, I have a homework assignment where I'll ask you to run through some, models, build some models in SPSS and answer some questions. But yeah, that's all the things that I wanted to cover for tonight. You have the PowerPoints and the presentation. When I get in tomorrow morning, I always upload the presentations to the Blackboard. It's a Panopto link. So that's where you'll find the videos if you need to go back. Okay?
Okay.
Cool, you guys. Good to see you and have a good night.
Thank you very much.
Thanks.